This is a space for winding down, for letting the day loosen its grip, and for allowing ideas to drift through your thoughts without needing to hold on to them too tightly. Whether you're listening with the lights already dimmed, or simply taking a quiet moment before rest, I am glad you are here. Tonight, we are going to sit with a question that sounds bold at first, maybe even a little rebellious, but does not need to be answered sharply or defensively. Instead, it can be approached the same way we approach sleep itself, slowly, patiently, with curiosity rather than resistance. The question is this: is the Big Bang Theory actually wrong? Not misunderstood, not incomplete, not simplified for textbooks, but wrong in a deeper sense. Or perhaps more gently, could it be less certain than we are often led to believe? Now, before your mind jumps ahead, before it starts assembling arguments or recalling headlines or imagining dramatic claims about scientists tearing up chalkboards, let's pause for a moment. This is not a debate. It is not an attack on science. It is not an attempt to replace one confident story with another. Instead, this is an invitation to look closely at how scientific ideas are formed, how they grow, and how they sometimes change shape when new questions refuse to stay quiet. The Big Bang is often presented as a settled fact, the opening scene of the universe complete with a date, a temperature, and a clear sequence of events. Everything began, we're told, around 13.8 billion years ago, in a state that was incredibly hot, incredibly dense, and expanding rapidly. From that early state came space, time, matter, galaxies, stars, planets, and eventually us. It is a powerful story, and like all powerful stories, it can feel reassuring to believe that the beginning of everything has already been explained. But science rarely works like a finished storybook. It works more like a notebook filled with crossed-out ideas, margin comments, and questions written in pencil rather than ink. The Big Bang Theory itself emerged not because scientists wanted a dramatic origin story, but because certain observations refused to fit old ideas about the universe being static and unchanging. Over time, those observations were organized into a framework that worked remarkably well. And yet, working well is not the same thing as being complete. It is not even the same thing as being unquestionably true in every possible sense. As we move through this exploration together, we will not rush to conclusions. We will not treat doubt as something dangerous or disrespectful. In science, doubt is often the starting point, not the enemy. Many of the greatest advances came from someone quietly asking, does this explanation really cover everything we see? That kind of question does not dismantle knowledge, it strengthens it. Before we go any further, let me ask you something simple. Where are you listening from right now? Are you somewhere familiar, like your bedroom or living room, or somewhere unusual, maybe traveling, maybe somewhere quiet and new? And what time is it for you at this moment? Early evening, late night, or that blurry hour where the day and night seem unsure which one is in charge? There is something fitting about thinking of the universe's beginning while each of us listens at a different point in our own small timeline. If you find this space calming, if the slow pace and gentle questioning help you unwind, you're welcome to show your support in the usual ways, with a like or a subscription. It helps this quiet corner of science reach others who might be looking for the same kind of peaceful curiosity. There is no rush, though. You can always decide later, or not at all. Now, let's ease into the question itself without tension, without drama. When people hear the phrase Big Bang, many imagine an explosion, something like a cosmic firework bursting outward into empty space. That image is vivid, but it is also misleading, and even scientists spend a surprising amount of time correcting it. The Big Bang, according to the theory, was not an explosion that happened at a particular point in space. It was an expansion of space itself, everywhere at once. There was no center. There was no surrounding emptiness for it to expand into. Space was not stretching into something else. Space was stretching, full stop. Even at this early stage, the language begins to strain. Words like before, after, beginning, and expansion all come from everyday experience, and yet they are being asked to describe something that has no direct everyday counterpart. That alone should make us cautious. When a theory relies on metaphors that can never be fully accurate, there is always room for misunderstanding, and sometimes for deeper problems hiding behind familiar phrases. One of the reasons the Big Bang Theory gained so much acceptance is that it does an impressive job of explaining several major observations at once. the expansion of galaxies away from one another, the faint glow of cosmic microwave background radiation, and the relative abundance of light elements like hydrogen and helium all fit neatly within its framework. These are not small details. They are significant, measurable features of the universe. Ignoring them would be irresponsible. And yet, even with these successes, there are questions that remain awkwardly unanswered. What exactly was expanding? What does it mean for time itself to have a beginning? Why did the early universe start in such a specific state? One that allowed galaxies and stars to form rather than collapsing back into nothing or flying apart too quickly. And perhaps most unsettling of all, what, if anything, came before? In many presentations of the Big Bang, these questions are set aside with phrases like, "we don't know yet," or "physics breaks down at that point." Those phrases are honest, but they also mark the edges of the theory's reach. When a theory repeatedly runs into a wall labelled unknown, it is worth asking whether that wall is temporary, or whether it suggests that the framework itself might need adjustment. There is another layer to this discussion that often goes unnoticed. Scientific theories are not just collections of equations and data. They are also shaped by assumptions, by the tools available at the time, and by the questions scientists think are worth asking. The Big Bang theory emerged in a period when physics was grappling with the consequences of general relativity and early cosmology. It was built using the best mathematics and observations available, but it was also built within certain conceptual limits. For example, the idea that the universe had a single, definite beginning fits comfortably with how human minds tend to think about stories. Everything starts somewhere. Every journey has a first step, but nature does not always cooperate with our narrative instincts. In other areas of physics, beginnings turn out to be far more complicated, sometimes dissolving entirely when examined closely. It is not unreasonable to wonder whether the universe's origin might belong to that category as well. You do not need to decide whether the Big Bang is right or wrong. There is no test at the end, no verdict required. Instead, you can simply notice how the question unfolds, how certainty and uncertainty coexist in science, and how even widely accepted ideas are often held together with more humility than popular explanations suggest. For now, let your attention settle. There is no need to hold on to every detail. If your thoughts wander, that is fine. You can always drift back when something catches your interest. The universe, after all, is not going anywhere, and neither is this question. For a long time now, the way we talk about the beginning of everything has followed a familiar pattern. It usually starts with confidence. Somewhere in the distant past, the universe began. Not gradually, not quietly, but decisively. A single moment when space, time, matter, and energy all came into existence together. From that moment onward, everything unfolded according to understandable rules, eventually leading to stars, planets, life, and curious minds asking how it all began. It is a story that feels neat, even comforting, because it gives the universe a clear opening line. That story did not emerge all at once. It was assembled slowly, shaped by observations, calculations, disagreements, and revisions. But once it took hold, it became more than just a scientific model. It became a cultural narrative. Textbooks, documentaries, museum exhibits, and casual conversations all began to repeat it in roughly the same way. The universe had a birthday. We knew when it happened, we knew roughly what it looked like, and we knew what followed next. There is nothing inherently wrong with telling science as a story. Humans understand the world through narratives. We connect causes to effects, beginnings to outcomes. When a scientific explanation fits neatly into that structure, it becomes easier to remember, easier to teach, and easier to share. Over time, though, the convenience of a story can blur the line between what a theory actually says and what we assume it must mean. When most people hear about the beginning of the universe, they imagine a moment that behaves like other beginnings they know. A spark that ignites a fire, a seed that grows into a tree, a starting gun that signals a race. Even when we are told that the Big Bang was not an explosion in space, the language surrounding it often pulls us back toward that image anyway. Words like birth, origin, and creation carry emotional weight, whether we intend them to or not. This is where the story begins to shape our expectations. If the universe began, then there must have been something like a before. If everything expanded from a hot, dense state, then it feels natural to ask what caused it. And if there was a cause, then perhaps there was something outside the universe that triggered it. These questions are not silly. They arise naturally from the way the story is framed. But they are also questions that the Big Bang Theory itself is not equipped to answer. In scientific terms, the Big Bang Theory describes the early evolution of the universe, not its ultimate origin in the philosophical sense. It tells us how the universe behaved when it was extremely hot and dense, how it expanded and cooled, and how simple particles eventually formed more complex structures. It does not explain why the universe exists at all, or why the laws of physics have the form they do. Those deeper questions often slip quietly into the gaps left by the story, where they take on a life of their own. As the narrative spread beyond the scientific community, those gaps were sometimes filled with assumptions rather than caution. Popular explanations smoothed over uncertainties to keep the story flowing. Diagrams showed a neat timeline starting at 0 and stretching forward to the present. Animations depicted a tiny glowing point rapidly expanding into galaxies. Over time, these representations became familiar enough that they started to feel literal, even though scientists themselves often emphasize their limitations. There's also the issue of authority. When a story is told repeatedly by experts, institutions, and trusted sources, it gains weight. It begins to feel settled. Questioning it can seem unnecessary or even contrarian, but in science, widespread acceptance does not mean a theory is immune to scrutiny. It means that, so far, it has explained observations better than its competitors. That distinction matters, especially when dealing with something as extreme and inaccessible as the earliest moments of the universe. The story of the beginning also reflects the tools we've used to observe the cosmos. Much of what supports the Big Bang Theory comes from looking outward and backward, using light that has travelled for billions of years. Telescopes allow us to see distant galaxies as they were long ago. Measurements of background radiation give us clues about conditions in the early universe. These are powerful tools, but they are indirect. We are reconstructing a past we cannot observe directly, using signals that have been altered by time, distance, and cosmic processes. Because of that, the story is always an interpretation, not a recording. It is a best-fit explanation based on available evidence, filtered through mathematical models and assumptions about how physical laws behave under extreme conditions. When the story is told too confidently, it can obscure that provisional nature. It can make it sound as though we are recounting a witnessed event rather than inferring a distant past from faint traces. Another reason the story holds such appeal is that it aligns with a broader human desire for origins. Many cultures have creation stories. Some involve gods, others involve cycles, chaos, or emergence from nothingness. The scientific story of the universe's beginning is often seen as a replacement for those older narratives. It offers a version that is grounded in observation rather than tradition. But even as it replaces them, it inherits some of their structure. There is a clear beginning. There is a sequence of events. There is a sense of progression from simplicity to complexity. These elements resonate with how humans have always tried to make sense of existence. That resonance can make the story feel intuitively right, even when parts of it are deeply counterintuitive from a physical standpoint. Within the scientific community, the story is usually told with more caveats. Researchers are careful to specify what the theory does and does not claim. They talk about epochs, parameters, and models rather than beginnings in the everyday sense. But those nuances often fade as the explanation moves outward into classrooms and media. The story becomes cleaner, more decisive, and less ambiguous. This is not necessarily a failure. Simplification is unavoidable when communicating complex ideas. The problem arises when simplification hardens into certainty, and certainty discourages curiosity. When the beginning of everything is presented as a solved problem, it leaves little room to explore alternative ideas or unresolved questions. There have always been scientists who are uneasy with the story as it is commonly told. Some objected to the implication that time itself began, arguing that this pushes physics into philosophical territory it cannot navigate. Others pointed out that the mathematics describing the earliest moments leads to infinities and breakdowns, signals that the theory is being pushed beyond its valid range. These concerns did not make the Big Bang Theory disappear, but they never fully went away either. Over time, the story has been adjusted to accommodate these issues. Concepts like cosmic inflation were introduced to explain why the universe appears so uniform and flat. Dark matter and dark energy were added to account for observed motions and expansion rates. Each addition improved the fit between theory and observation, but also made the story more complex and in some ways more fragile. It is worth noticing how these additions are often described. They are rarely framed as signs of trouble. Instead, they are presented as refinements, extensions, or missing pieces. That framing keeps the core story intact, even as it grows increasingly elaborate. Whether that is a strength or a warning sign depends on how one interprets the role of theories in science. From one perspective, this is exactly how science progresses. A basic framework is established, and then details are filled in as new evidence emerges. From another perspective, the growing number of unseen components can raise questions about whether the framework itself is the best possible one. At what point does adding complexity suggest that the underlying story might need rethinking? The way the beginning of everything is told also affects how people think about the future of cosmology. If the origin is settled, then the remaining work is refinement. Better measurements, more precise data, smaller error bars. If the origin is still open, then deeper conceptual changes may lie ahead. Those two outlooks lead to very different scientific cultures. None of this means that the Big Bang theory is obviously wrong or on the verge of collapse. It means that the story we tell about it may be more confident than the evidence strictly allows. It means that the narrative has taken on a life of its own, shaped by repetition, pedagogy, and cultural expectations. As you listen to this, you might notice your own reactions to the idea of questioning the beginning story. Perhaps there is curiosity. Perhaps there is discomfort. Perhaps there is a sense that some ideas feel too foundational to question. All of those reactions are understandable. The beginning of everything is not a small topic. It touches on identity, meaning, and our place in the universe. The story we have been telling ourselves did not emerge overnight, and it will not change overnight either. What matters is recognizing that it is a story shaped by evidence, interpretation, and human perspective, not a final word carved into the structure of reality. When people say the Big Bang, they often feel as though they are naming a single event, something sharp and dramatic that happened once and then was over. The phrase itself encourages that impression. It sounds sudden. It sounds violent. It sounds like the universe arrived with a noise. But when scientists use the term carefully, they are not describing a bang in the ordinary sense at all. They are referring to a model, a framework, a way of describing how the universe behaved when it was very different from how it is now. At its core, the Big Bang theory is not a theory about how the universe came into existence from nothing. It is a theory about how the universe has evolved from an early, hot, dense state into its current, cooler, more spread out form. That distinction is easy to miss because everyday language tends to blur it. Saying, the beginning of the universe feels natural, but it quietly adds claims that the theory itself does not strictly make. What scientists mean by the Big Bang is that, when we trace the expansion of the universe backward using the equations of general relativity and modern cosmology, we find that the universe becomes denser, hotter, and more compact the farther back we go. Galaxies move closer together. Radiation becomes more energetic. Matter exists in simpler forms. Eventually, the mathematics points toward an extreme state, where densities and temperatures become enormous. That is the region we label the Big Bang. What they do not mean is that there was a point in space where everything exploded outward into emptiness. There was no center of the expansion. Every region of space was closer together than it is now. From the perspective of any galaxy, all other galaxies appear to be moving away, not because they were flung outward from a central blast, but because the space between them has been stretching. This is one of the most persistent misunderstandings. Even people who are familiar with the theory sometimes imagine the universe expanding into something, like a balloon inflating into surrounding air. In the cosmological picture, there is no surrounding space that the universe is growing into. Space itself is what is expanding. Asking what the universe is expanding into is a bit like asking what the surface of a balloon is expanding into if you only live on the surface. From within the system, the question does not quite apply. Another important clarification concerns time. When people hear that the Big Bang happened 13.8 billion years ago, They often imagine a timeline stretching backward into a moment before that. They ask what existed before the Big Bang, what caused it, or what was happening just prior. These questions feel unavoidable, because our experience of time always includes a before. However, according to the standard cosmological model, time itself is part of what is described by the expansion. When we extrapolate backward to the earliest moments the equations can handle, time as we understand it reaches a boundary. That does not necessarily mean time truly began at that moment. It means that our current theories cannot meaningfully describe anything earlier. This is an important difference. Saying we cannot describe what came before is not the same as saying there was nothing before. The first is a statement about the limits of our models. The second is a statement about reality itself. The Big Bang theory makes the first claim, not the second, even though popular explanations often slide toward the second without much warning. The phrase Big Bang also tends to suggest a singular, sharply defined instant. In practice, the theory describes a sequence of conditions over a very short but non-zero span of time. Physicists talk about fractions of a second after the Big Bang, during which different processes occurred. Forces separated, particles formed, energy cooled. Even in the earliest moments we can describe, there is structure and change, not a frozen point. The idea of a singularity, an infinitely dense point where the equations blow up, is often treated as the beginning itself. In reality, most physicists regard singularities as signs that a theory has reached its limit. In other areas of physics, when equations produce infinities, it usually means the model is incomplete. Something important has been left out, often a deeper theory that smooths out the extremes. The singularity associated with the Big Bang is widely viewed in this way, not as a literal description of reality. What the Big Bang does mean, very concretely, is that the universe was once much hotter and denser than it is now. This claim is supported by several independent lines of evidence. One of the strongest is the cosmic microwave background, a faint glow of radiation that fills the universe. This radiation is remarkably uniform, with tiny variations that carry information about early cosmic conditions. Its existence and properties match predictions made by Big Bang cosmology long before it was observed in detail. Another piece of evidence comes from the relative abundances of light elements. Hydrogen, helium, and traces of lithium appear in proportions that align with calculations of nuclear reactions occurring in a hot early universe. These calculations depend on well-tested physics, and their agreement with observation is one of the theory's major successes. When scientists point to these achievements, they are not exaggerating. The Big Bang model explains a great deal with a relatively compact set of assumptions. Still, even here, it is important to be precise about what is being explained. The theory accounts for the universe's expansion history, its large-scale structure, and certain relics of its early state. It does not explain why the laws of physics take their particular form. It does not explain why the initial conditions were suitable for galaxies and life to emerge. It does not explain whether the universe is unique or one of many. Those questions lie outside its scope. Another thing people often assume is that the Big Bang theory represents a single, unchanging idea. In fact, it has evolved significantly over time. Early versions were simpler and left many puzzles unresolved. Later developments added mechanisms like cosmic inflation, which proposes a brief period of extremely rapid expansion very early on. Inflation helps explain why the universe appears so uniform and why its geometry seems close to flat. It also introduces new assumptions and new unanswered questions. When inflation is discussed, the phrase "the Big Bang" becomes even more ambiguous. Does it refer to the moment inflation began, the moment it ended, or the subsequent hot, dense phase? Different researchers use the term differently, sometimes without clarifying which phase they mean. This can create confusion even within scientific discussions, let alone in public explanations. There is also a tendency to treat the Big Bang as synonymous with the origin of everything, including the laws of physics themselves. Some speculative ideas suggest that physical laws may have emerged or changed during the early universe. Others assume the laws were already in place. The standard Big Bang model does not settle this issue. It typically assumes known laws and applies them backward as far as they seem reliable. Beyond that, it remains silent. Because of this, criticisms of the Big Bang often talk past what the theory actually claims. When someone says, the Big Bang doesn't explain what caused the universe, they are pointing out a real gap, but not necessarily a flaw within the theory's intended domain. When someone says, the Big Bang violates common sense, they may be reacting to misleading imagery rather than to the mathematics itself. On the other hand, defenders of the theory sometimes overstate its reach. They may speak as though the origin problem has been solved, when in reality it has been reframed. The language used can give the impression that science has answered questions it has actually set aside for future work. All of this makes the phrase, the Big Bang, do a lot of heavy lifting. It compresses a complex set of ideas, equations, observations, and assumptions into 2 words that invite misunderstanding. It is useful shorthand, but it is also a source of confusion. As you sit with this, it may help to think of the Big Bang not as a moment, but as a description of a trend. The universe has been expanding and cooling. It was once denser and hotter. Beyond a certain point, our current descriptions lose their reliability. That is the heart of the model. Everything else, the imagery, the timeliners, the dramatic language, are ways of trying to make that abstract picture accessible. This distinction becomes especially important when people ask whether the Big Bang is wrong. If by wrong we mean that the universe is not expanding from a hotter, denser past, then the evidence strongly suggests that it is not wrong in that sense. If by wrong we mean that it provides a complete account of the universe's ultimate origin, then it was never meant to do that in the first place. Recognizing what we mean and what we do not mean when we say the Big Bang allows the discussion to become calmer and more precise. It shifts the focus away from dramatic claims and toward the actual content of the theory. It also opens the door to asking better questions about the limits of our models and the possibilities that might lie beyond them. Long before the phrase Big Bang became familiar, long before it settled into textbooks and documentaries, scientists were not looking for a beginning at all. They were trying to understand what kind of universe they were living in right now. The idea that the universe might have a history, that it might change on the larger scales, was not obvious. For centuries, the prevailing assumption was that the cosmos was eternal and largely unchanging. Stars might be born and die, planets might form and fade, but the overall structure of the universe was assumed to be stable, fixed, and timeless. What shifted that assumption was not a single dramatic discovery, but a collection of strange, often unsettling observations that did not fit comfortably within the older picture. None of them announced themselves as evidence of a cosmic beginning. At first, they were puzzles, technical annoyances, odd results that made astronomers pause, recheck their instruments, and wonder whether they had made mistakes. One of the earliest cracks appeared when astronomers began to study the light coming from distant galaxies in more detail. Light carries information not just about where something is, but how it is moving. When an object moves away from us, the light it emits is stretched, shifting toward the red end of the spectrum. This effect, known as redshift, was already understood in other contexts. It had been measured in stars moving within our own galaxy. What surprised astronomers was how consistently it appeared in galaxies far beyond the Milky Way. As telescopes improved and observations expanded, a pattern began to emerge. The farther away a galaxy was, the more its light appeared to be redshifted. At first, this was interpreted cautiously. Distance measurements were uncertain. The universe beyond our galaxy was still largely unexplored. But as the data accumulated, the trend became harder to dismiss. Distant galaxies were not just moving randomly. They were, almost without exception, moving away. Even more unsettling was the fact that this recession did not seem to have a preferred direction. Galaxies were not streaming away from a central point in the sky. Instead, wherever astronomers looked, galaxies appeared to be receding from each other. From Earth's perspective, everything else seemed to be moving away, as though the universe itself was swelling. This observation alone did not demand a Big Bang. It did, however, challenge the idea of a static universe. If galaxies were moving apart, something had to explain why. One possibility was that galaxies were simply flying through space, like debris from some ancient explosion. Another possibility, more subtle and far more radical, was that space itself was changing. The mathematical framework for that second idea had already been developed, though few realized how relevant it would become. General relativity, with its flexible conception of space and time, allowed for solutions in which the universe could expand or contract. When those equations were applied to cosmology, they naturally produced models of a dynamic universe. At the time, even the theory's creator reportedly found this unsettling and attempted to modify the equations to keep the universe static. The mathematics suggested expansion. The observations suggested recession. Slowly, reluctantly, the pieces began to align. Still, expansion alone does not automatically imply a beginning. An expanding universe could, in principle, have been expanding forever. The idea that expansion pointed back to a hot, dense early state required further evidence. That evidence arrived in a form so quiet and unassuming that it was almost missed entirely. In the middle of the 20th century, engineers working with radio antennas stumbled upon a persistent background noise. No matter where they pointed their equipment, no matter the time of day or the season, a faint hiss remained. At first, it was treated as a technical problem. The antenna was cleaned, components were replaced, even nesting animals were blamed. Nothing removed the signal. Eventually, it became clear that the noise was not coming from Earth, the Sun, or the Milky Way. It was coming from everywhere, uniformly. The sky itself seemed to glow faintly in radio frequencies. This glow turned out to be one of the most significant discoveries in modern cosmology. According to theoretical work done years earlier, a universe that had once been extremely hot should still carry a thermal afterglow. As the universe expanded and cooled, that radiation would stretch into longer wavelengths, eventually becoming microwave radiation. The predicted temperature was only a few degrees above absolute zero. The measured signal matched that prediction remarkably well. This radiation, now known as the cosmic microwave background, did not just exist, it had specific properties. Its spectrum matched that of a cooling thermal source. Its uniformity suggested that the early universe had been remarkably even in temperature. Tiny variations in that uniformity hinted at the seeds of later structures, the slight differences in density that would eventually grow into galaxies and clusters. It is difficult to overstate how strange this evidence was. The universe, it seemed, remembered being hot. It carried a fossil imprint of an earlier state, one that could not be explained by stars or galaxies alone. This was not light emitted by objects within the universe. It was light emitted by the universe itself long before stars had formed. Another line of evidence came from the relative amounts of certain elements found throughout the cosmos. Hydrogen and helium dominate the universe by a wide margin. Heavier elements are present, but in much smaller quantities. This distribution is not arbitrary. Nuclear physics predicts that in a hot, dense early universe, only certain elements could form in significant amounts. The predicted ratios of hydrogen to helium matched observations with surprising accuracy. Stars can produce heavier elements over time, but they cannot easily account for the observed abundance of helium across the universe. The simplest explanation was that much of this helium formed very early, under conditions that no longer exist. Again, the universe appeared to be carrying chemical evidence of a hotter, denser past. Individually, each of these observations might have been explained away with enough creativity. Together, they formed a pattern that was difficult to ignore. Expansion, background radiation, elemental abundances, all pointed toward a universe that was once radically different. What made this evidence particularly compelling was that it came from different domains of physics. Astronomy, thermodynamics, nuclear physics, and relativity all converged on the same broad picture. That kind of convergence is rare. When independent lines of inquiry point in the same direction, scientists tend to pay attention. Even so, acceptance was not immediate or universal. Alternative ideas existed. Some proposed steady-state models in which the universe expanded but maintained constant density through the continuous creation of matter. These models could explain expansion without a beginning. For a time, they competed seriously with Big Bang cosmology. The cosmic microwave background dealt a severe blow to those alternatives, explaining that radiation without an early hot phase required increasingly contrived assumptions. Over time, the balance of evidence shifted decisively. The Big Bang framework, despite its unanswered questions, explained more with fewer assumptions. It is important to notice what kind of evidence convinced scientists. It was not philosophical appeal. It was not a desire for a dramatic origin story. It was a set of measurements that stubbornly refused to fit a timeless universe. At the same time, this evidence has limits. It tells us that the universe was hot, dense and expanding. It does not tell us how or why those conditions arose. It does not tell us whether they were the first conditions or simply one phase in a longer story. The evidence supports a specific range of conclusions, not every conclusion that people sometimes draw from it. There's also an important asymmetry in how this evidence works. It supports the idea that the universe evolved from a hot, dense state. It does not directly observe that state itself. We infer it. We reconstruct it. We build models that, when run backward, match the traces we see today. This reconstruction relies on assumptions about how physical laws behave under extreme conditions. Most of the time, those assumptions work well, but there are regimes, especially at very high energies and densities, where existing theories are known to be incomplete. When scientists speak cautiously about the earliest moments, this is why. The strange evidence that led to the Big Bang theory is strong, but it is not omnipotent. It answers certain questions very well. It leaves others open. Recognizing this balance is essential for understanding both why the theory became dominant and why questions about its ultimate completeness remain reasonable. As you sit with this, it may help to let go of the idea that scientists were convinced by a single proof. Instead, imagine a slow accumulation of clues, each one nudging the picture in the same direction. None of them demanded a beginning outright. Together they suggested a universe with a deep past, one that could be traced back to conditions far removed from anything we experience today. One of the most stubborn images associated with the Big Bang is the idea of an explosion. It is an image that sneaks in quietly, reinforced by language, illustrations, and even the name itself. A bang suggests a center, a violent outward rush, debris flying into surrounding emptiness. It feels intuitive, almost unavoidable, because explosions are something we understand from everyday life. Fireworks burst, bombs detonate, engines backfire. When we hear that everything began with a big bang, the mind fills in the rest automatically. And yet, this picture is almost completely wrong. The misunderstanding is not a small detail or a pedantic correction. It goes to the heart of what the theory actually describes. Clearing it up changes how we think about space, motion, and the very meaning of expansion. It also reveals why so many questions about the Big Bang feel confusing or unanswerable when framed in the wrong way. To begin untangling this, it helps to set aside the idea of an explosion entirely. An explosion happens at a location. It occurs within space. There is something before it, something around it, and something afterward. A firework explodes at a point in the sky. Shrapnel from an explosion moves through the surrounding air. Even the largest explosions we can imagine still take place inside a pre-existing environment. The expansion described by the Big Bang theory is fundamentally different. It is not something happening in space. It is something happening to space. This distinction sounds subtle at first, but it changes everything. When cosmologists talk about the universe expanding, they're not saying that galaxies are flying outward through a fixed cosmic arena. They're saying that the distances between galaxies are increasing because the fabric of space itself is stretching. The galaxies are, in a sense, being carried along rather than hurled outward. A common way to picture this is with an analogy, though even analogies have limits. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart. From the perspective of any one dot, all the others appear to be receding. There is no special dot at the center of the expansion on the surface itself. The expansion happens everywhere on the surface at once. Importantly, the dots are not moving across the surface under their own power. The surface they sit on is changing. In the cosmological case, galaxies are like those dots. They are mostly at rest relative to their local space, but the space between them grows. That is why distant galaxies appear to recede faster than nearby ones. It is not because they were flung outward with greater force. It is because there is more expanding space between us and them. This is why astronomers can measure a consistent relationship between distance and recession speed. The farther away a galaxy is, the more space there is between us and it, and the more that space has expanded during the light's journey to us. If the universe were the result of an explosion, we would expect a very different pattern. There would likely be a central region with debris moving fastest, slowing as it spreads out. There might be observable asymmetries, preferred directions, or gradients pointing back to a center. None of this is observed. On large scales, the universe looks remarkably uniform in every direction. This uniformity was one of the clues that pushed scientists away from explosion-based thinking in the first place. An explosion in space produces structure and direction. The observed universe does not behave that way. Another common question that arises from the explosion picture is, what did the universe explode into? It is a natural question, and one that feels unanswered in many explanations. But within the correct framework, it is not really a meaningful question. If space itself is expanding, there is no external container that it is expanding into. There is no outside edge moving into emptiness. This is deeply unintuitive because we are used to objects having boundaries and surroundings. Our experience is built entirely within space, so imagining space itself as dynamic requires letting go of familiar mental scaffolding. When people ask what lies beyond the edge of the universe, or what space is expanding into, they're often unknowingly clinging to the explosion metaphor. Within the standard cosmological model, the universe does not need an outside. It is not embedded in a larger space in the way objects are embedded in rooms. Space is the arena, not a thing within an arena. This does not mean the universe must be infinite, nor does it mean it must have edges. Both finite and infinite models are possible, depending on the geometry of space. What matters here is that expansion does not require a surrounding void. Another misunderstanding tied to the explosion idea involves the notion of a starting point. People often imagine a tiny, incredibly dense speck that then blew outward, becoming larger over time. This image suggests that the early universe was small in size, confined to a particular region. In reality, the theory does not require the universe to have been small in that sense. The universe could have been infinite even in its earliest hot, dense phase. Expansion describes how distances change, not how large the universe is overall. An infinite universe can expand just as easily as a finite one. Every distance increases, even though there is no boundary enclosing the whole. This again clashes with explosion imagery, which relies on finite objects growing outward. When that imagery is applied to cosmology, it creates confusion where none is required. There is also a misconception that expansion means everything is moving away from everything else in the same way. On smaller scales, this is not true. Galaxies bound together by gravity do not expand away from one another. Stars within galaxies do not drift apart because of cosmic expansion. Atoms do not stretch. The expansion becomes noticeable only on very large scales, where gravity is weak enough that the stretching of space dominates. An explosion, by contrast, would affect everything within its range. It would tear structures apart indiscriminately. The fact that cosmic expansion leaves local structures intact is another sign that we are dealing with a very different phenomenon. Understanding this helps resolve another common confusion. People sometimes imagine that galaxies are racing through space at incredible speeds, approaching or exceeding the speed of light. In reality, the apparent superluminal recession of very distant galaxies arises because space itself is expanding. The galaxies are not locally breaking the speed limit set by relativity. The rule applies to motion through space, not to the expansion of space. Again, this distinction disappears if one insists on thinking in terms of an explosion. Explosions involve objects moving through space, subject to familiar constraints. Expansion involves the geometry of space changing, which plays by different rules. The explosion picture also encourages the idea that the Big Bang was loud, bright, and chaotic in a way that resembles a detonation. In truth, there was no sound because sound requires a medium, and there were no ears to hear it even if there had been. The early universe was hot and energetic, but its behavior was governed by physical laws, not violent randomness. The word bang was originally coined somewhat mockingly by a scientist who favored a different cosmological model. It stuck because it was memorable, not because it was accurate. Over time, the name shaped public understanding more than many of the careful explanations that followed. Once the explosion metaphor takes hold, it becomes difficult to ask sensible questions. People ask where the explosion happened, what caused it, and what the debris is expanding into. These questions feel profound, but they are based on a category error. They treat expansion as motion through space rather than change of space. Clearing up this misunderstanding does not answer every question about the universe's early history. In fact, it often exposes new ones. If space itself is expanding, what exactly is space? Why can it stretch? What determines the rate at which it expands? These are deep questions that lead directly into modern cosmology and fundamental physics. They also connect to unresolved problems. For example, the equations describing expansion allow many possible behaviors. The observed expansion rate, its acceleration, and its early rapid phases are not uniquely determined by simple assumptions. Additional ingredients, like dark energy and inflationary fields, are introduced to account for what we see. Here too, misunderstanding expansion as an explosion can hide important subtleties. If one imagines a single violent event that set everything in motion, it feels natural to expect expansion to slow over time as gravity pulls things back together. The discovery that expansion is accelerating came as a surprise, partly because it does not fit that intuition. In the correct framework, acceleration is a property of space's dynamics, not leftover momentum from a blast. As you sit with this corrected picture, you may notice how it softens some of the emotional weight attached to the idea of a beginning. An explosion suggests abruptness and drama. Expansion suggests gradual change. Even if that change was extreme in the early universe, it feels less like a cosmic accident and more like a process governed by structure. This shift also affects how people interpret questions about whether the Big Bang could be wrong. If one rejects the explosion image, much of what seems implausible or nonsensical about the theory falls away. What remains is a more precise, less sensational claim about the universe's evolution. At the same time, rejecting the explosion does not mean accepting everything uncritically. The expansion picture still leads back to conditions where current theories struggle. As distances shrink and densities rise, our mathematical descriptions approach regimes where quantum effects cannot be ignored. The fact that expansion is not an explosion does not magically resolve the mystery of the earliest moments. In some ways, clearing up this misunderstanding makes the remaining questions sharper rather than fuzzier. If there was no blast, no center, no outward rush into emptiness, then the origin problem becomes more abstract. It is no longer about an event happening somewhere. It is about why space has the properties it does, and why those properties led to the expansion history we observe. These are quieter questions, less cinematic but arguably more profound. They require thinking about geometry, energy, and the structure of physical law itself. They are also the questions where the Big Bang theory begins to feel less like a complete story and more like a chapter within a larger unfinished one. As we move forward, it will be useful to keep this corrected picture in mind. Many of the criticisms and alternatives to the Big Bang make sense only once the explosion metaphor has been discarded. Without doing that, it is too easy to argue against a caricature rather than against the theory as it is actually used. The idea that the universe expanded without exploding is strange, but it is also one of the most firmly grounded aspects of modern cosmology. Accepting it does not require abandoning common sense, so much as recognizing where common sense, shaped by everyday experience, stops being a reliable guide. Even after the explosion metaphor has been set aside, even after expansion is understood as something happening to space rather than within it, a number of questions remain that refuse to settle quietly. These questions are not fringe objections or philosophical nitpicks. They arise naturally from within the Big Bang framework itself, once it is taken seriously and followed as far as it can go. They are the places where the theory does not quite break, but where it begins to thin out, where explanations become tentative, conditional, or simply unavailable. One of the most persistent of these questions concerns beginnings in a more fundamental sense. If the universe was once in an extremely hot, dense state, and has been expanding ever since, it is tempting to imagine that this description can be extended all the way back to a first moment. But when scientists actually try to do this using known physics, they encounter a wall. Temperatures and densities rise without bound. Quantities blow up to infinity. Time itself seems to shrink towards zero. At that point, the equations no longer behave in a physically meaningful way. This breakdown is often described using the language of a singularity. A singularity is not an object or a place. It is a signal that a mathematical model has been pushed beyond the conditions under which it can be trusted. In other areas of physics, singularities tend to disappear when a deeper theory replaces an older one. The center of an atom once appeared singular, until quantum mechanics resolved it. Electrical forces once diverged at small distances until new principles intervened. In cosmology, the singularity associated with the Big Bang is widely interpreted in this same spirit. It marks the edge of our current understanding, not necessarily the edge of reality. The uncomfortable part is that despite decades of work, there is still no widely accepted theory that cleanly replaces the Big Bang description at those earlier scales. We know something is missing, but we do not yet know what it is. This leads directly to another uneasy question. Did time itself actually begin? The standard cosmological equations suggest that time, as defined within the model, cannot be extended beyond the earliest hot, dense phase. But this does not settle the matter. It simply reflects the structure of the equations. Whether time truly had a beginning, or whether this is a limitation of the mathematical framework, remains open. The question is uncomfortable because it challenges the very tools used to answer it. Physics relies on time to describe change. Asking what happened before time existed risks turning language against itself. Some physicists argue that the question is meaningless. Others suspect that time may emerge from deeper, timeless processes. Still others propose that time existed before the Big Bang in some altered or hidden form. None of these possibilities has been decisively confirmed. The Big Bang theory, by itself, does not adjudicate between them. It describes a phase of cosmic history. It does not explain why that phase occurred, or whether it was the first of its kind. Closely related to this is the question of cause. Human reasoning is deeply causal. We expect events to have explanations rooted in prior events. When presented with a theory that seems to describe the origin of everything, it is almost impossible not to ask what caused it. What set the expansion in motion? Why did the universe begin in a state that allowed it to evolve as it did? Within the Big Bang framework, these questions have no clear answers. The theory does not identify a triggering mechanism. It does not describe a prior state that led naturally to the hot, dense beginning. Attempts to supply such explanations usually require going beyond the standard model of cosmology, introducing speculative ideas that are still under investigation. Some researchers propose quantum processes that could give rise to universes spontaneously. Others suggest that the Big Bang was not the first event, but a transition from an earlier phase, such as a contracting universe or a previous cycle. These ideas are intriguing, but they are not yet established in the same way as the expansion history itself. Another uncomfortable issue lies in the initial conditions of the universe. Even if one accepts that the universe began in a hot, dense state, the specific properties of that state are puzzling. The early universe appears to have been remarkably uniform. Temperature differences across vast regions were extremely small. Density variations were tiny. Yet those small variations were precisely tuned to allow structure to form later. This apparent fine balance raises questions. Why was the universe so smooth early on? Why were the initial fluctuations neither too large nor too small? If they had been much larger, the universe might have collapsed quickly into black holes. If they had been much smaller, galaxies might never have formed. Cosmic inflation was proposed partly to address this issue. A brief period of rapid expansion early in the universe's history could smooth out irregularities and explain the observed uniformity. Inflation also helps explain why the geometry of the universe appears close to flat. But inflation introduces its own questions. What caused inflation to start? What caused it to end? Why did it produce the specific pattern of fluctuations we observe? Inflation works well as a mechanism, but it shifts the discomfort rather than eliminating it. The need for special initial conditions is replaced by the need for special inflationary conditions. Some versions of inflation lead naturally to multiverse scenarios in which many regions of space undergo inflation in different ways. This can explain certain observations statistically, but it also raises philosophical and scientific concerns about testability. Another question that sits uneasily within the Big Bang framework involves the laws of physics themselves. The theory assumes that known physical laws apply, at least approximately, during the early universe. But at extremely high energies, those laws are expected to merge or change. Gravity, quantum mechanics, and other forces are described by theories that are not yet fully unified. This creates a gap. The Big Bang model relies on general relativity to describe expansion, but general relativity does not incorporate quantum effects. At early times, quantum effects cannot be ignored. The lack of a complete theory of quantum gravity means that descriptions of the very early universe are provisional at best. As a result, statements about what happened at the earliest times often rest on extrapolations that may not hold. Scientists are aware of this, and they phrase their conclusions carefully in technical contexts. In popular explanations, however, this caution can be lost, giving the impression of certainty where there is still active uncertainty. There is also the matter of entropy, which connects cosmology to thermodynamics. The universe appears to have started in a low-entropy state. This is surprising because high-energy systems often correspond to high entropy. The fact that the early universe was both hot and highly ordered is one of the deepest puzzles in modern physics. This low-entropy beginning underlies the arrow of time. It explains why time seems to flow in one direction, from past to future, with increasing disorder. But the Big Bang theory does not explain why the universe began in such a special state. It takes it as a given. Some physicists argue that this question may be unanswerable within current frameworks. Others suspect that a deeper theory will reveal a reason. For now, it remains one of the most uncomfortable aspects of the story, because it touches not just on cosmology, but on the nature of time itself. Another source of unease is observational limitation. The universe has a finite age, and light travels at a finite speed. This means there is a limit to how much of the universe we can observe. Beyond a certain distance, regions of space are causally disconnected from us. We cannot receive information from them, even in principle, given the universe's expansion. This cosmic horizon means that our picture of the universe is necessarily incomplete. We infer global properties from a limited sample. While there are good reasons to believe that the observable universe is representative of the whole, this assumption cannot be directly verified. The Big Bang theory relies on extrapolating local observations to the entire cosmos. Most of the time, this extrapolation works remarkably well. But when dealing with origins, even small uncertainties can loom large. The farther back we push our models, the more they depend on assumptions that cannot be directly tested. There is also the issue of uniqueness. Is our universe the only one? The Big Bang theory does not require multiple universes, but some of its extensions suggest them. Inflationary models, quantum cosmology, and string theory landscapes all hint at the possibility of many universes with different properties. If this is the case, then the Big Bang might not be a unique beginning, but one instance among many. This idea challenges the notion that cosmology can provide a single, definitive account of existence. It also complicates the question of explanation. Why does our universe have the properties it does? Perhaps because only such universes allow observers to ask the question. Whether one finds this satisfying or troubling often depends on philosophical temperament. Scientifically, the multiverse remains speculative, but its appearance as a possible implication highlights the way unresolved questions multiply as we probe deeper. None of these discomforts invalidate the Big Bang theory as a description of cosmic expansion. They do, however, limit what it can claim. The theory works extremely well within a certain domain. Outside that domain, it becomes suggestive rather than definitive. Recognizing this does not weaken science. It clarifies its boundaries. It reminds us that theories are tools, not final answers. They organize evidence, make predictions, and guide further inquiry. They are not required to satisfy every curiosity, especially those that reach beyond current observational and theoretical reach. You may notice that these uncomfortable questions do not point in a single direction. They do not all suggest the same alternative. Instead, they form a landscape of uncertainty surrounding the Big Bang's earliest moments. Some questions may eventually be answered by new data. Others may require new conceptual frameworks. Some may remain open indefinitely. What matters for now is that these questions exist, that they are taken seriously by scientists, and that they arise not from misunderstanding the theory, but from understanding it well enough to see where it stops. When people hear that the universe has a beginning, the mind almost automatically tries to look past it. There is a strong pull to imagine something on the other side of that boundary, some earlier state, some hidden chapter just out of view. This instinct is so natural that it shows up even in the language scientists use, despite their best efforts to be precise. Phrases like, "before the Big Bang," slip into conversations, lectures, and articles, even though they point directly at a region where the theory itself falls silent. The uncomfortable truth is that, Within the standard Big Bang framework, there is a limit beyond which the theory simply cannot see. It is not that there is a veil we have not yet lifted or a telescope we have not yet built. It is that the mathematical tools used to describe the universe lose their meaning when pushed too far back. The equations do not smoothly extend into an earlier chapter. They stop offering sensible answers altogether. This is one of the most difficult ideas to sit with, because it runs against how we normally think about knowledge. Usually when we say we cannot see something, we assume it is because of a practical limitation. We lack data, we lack resolution, we lack the right technology. In this case, the limitation is deeper. It is built into the structure of the theory itself. The Big Bang model relies heavily on general relativity to describe how space and time behave on cosmic scales. General relativity treats space and time as a flexible geometry that responds to energy and matter. It works extraordinarily well for describing planets, stars, galaxies, and the large-scale expansion of the universe, but it was never designed to handle situations where quantum effects dominate. As we trace the universe backward toward earlier and earlier times, we inevitably reach conditions of extreme density and temperature. At those scales, quantum effects are no longer small corrections, they become central. Particles behave less like points and more like probabilistic clouds. Energy fluctuates in ways that classical descriptions cannot capture. In this regime, general relativity on its own is no longer sufficient. When scientists say the theory cannot see past a certain point, this is what they mean. The mathematical framework breaks down. Space and time, as defined by the theory, stop behaving in ways that can be reliably calculated. The notion of a smooth timeline extending backward becomes questionable. This breakdown is often associated with the idea of a singularity. In the equations, quantities such as density and curvature grow without bound as one approaches the earliest moment. Time appears to shrink towards zero. But most physicists do not believe that reality actually contains infinities in this sense. Instead, infinities are taken as warning signs. They tell us that a theory is being asked to describe something it was never equipped to handle. There is a temptation to treat the singularity as a real event, the literal beginning of everything. This temptation is understandable, because the equations seem to point there, but history suggests caution. In other areas of physics, singularities have repeatedly turned out to be artifacts of incomplete theories. When a deeper framework is found, the singularity often dissolves into something finite and well-behaved. This is why many cosmologists are careful with their language. They do not say that the universe definitely began at singularity. They say that the Big Bang model cannot be extended past a certain point without new physics. That difference matters. The phrase, "before the beginning," is especially tricky. If time itself is part of what the Big Bang model describes, then asking what happened before time existed may not be a meaningful question within that framework. It is a bit like asking what is north of the North Pole. The question assumes a continuation of a concept that has reached its definitional limit. This does not mean that nothing existed, or that no earlier state is possible. It means that our current way of describing time cannot reach that far. There could be something before the Big Bang in a sense that does not align with everyday notions of before and after. Or there could be a different structure altogether, one in which time behaves differently or emerges from more basic relationships. Various ideas have been proposed to fill this blind spot. Some suggest that the universe went through a contracting phase before expanding, making the Big Bang a transition rather than a creation. In these scenarios, the universe shrinks, reaches a minimum size, and then rebounds. The expansion we observe would be the aftermath of that bounce. Other proposals imagine a universe that is eternal, with no beginning or end, but with phases that resemble Big Bang-like events. In such models, what we call the Big Bang is just one episode in a much longer story. The universe may have experienced many expansions and contractions over vast timescales. There are also ideas rooted in quantum cosmology, where the universe arises from quantum processes that do not require a classical notion of time at all. In these views, the universe does not begin in the usual sense. Instead, it transitions from a quantum state that cannot be described using ordinary temporal language. These ideas are fascinating, but they remain speculative. They are attempts to peer beyond the edge of the Big Bang model using incomplete tools. None of them has yet achieved the level of empirical support that the expansion history of the universe enjoys. That does not make them wrong. It simply places them in a different category of scientific inquiry. What is important here is recognizing that the Big Bang theory itself does not choose between these possibilities. It does not tell us whether there was a before. It does not tell us whether the universe emerged from nothing, from something, or from a state that does not fit either label. It tells us what happened after the universe entered a phase we can model with confidence. This limitation often frustrates people, because the beginning feels like the most important part of the story. If we know how everything evolved, why can we not know how it started? The answer lies in the nature of scientific explanation. Science builds models that connect causes to effects within a defined domain. When that domain ends, the explanations end with it. There is also a psychological dimension to this discomfort. Humans are deeply oriented toward origins. We ask where things come from. We trace lineages. We look for first causes. When confronted with a theory that refuses to provide a clear origin, it can feel unsatisfying, even evasive. But this refusal is not a flaw in the theory. It is an honest acknowledgement of its limits. Pretending to know what lies beyond those limits would be far more misleading than admitting uncertainty. Another reason the theory cannot see past the beginning has to do with observation. The universe has been expanding for a finite amount of time. Light from the earliest observable epoch has only just reached us. Beyond that, earlier signals are either too energetic, too scrambled, or simply inaccessible given the universe's evolution. The cosmic microwave background represents the oldest light we can observe directly. It comes from a time when the universe became transparent to radiation. Before that, the universe was opaque. Photons could not travel freely. Any information from earlier times is hidden from direct observation. This observational horizon is not just a technical inconvenience. It is a fundamental feature of an expanding universe. Even with perfect instruments, there are limits to what can be seen. Models can extrapolate beyond those limits, but extrapolation is not observation. This means that questions about what happened before the Big Bang are doubly constrained. The theory lacks the tools to describe that regime, and the universe lacks a clear way to communicate information from it. Any answer must rely on indirect reasoning, mathematical consistency, and philosophical assumptions about what kinds of explanations are acceptable. Some scientists argue that this makes the question unscientific. Others disagree, pointing out that many areas of physics began as speculative attempts to explain phenomena beyond immediate observation. The boundary between scientific and philosophical inquiry is not always sharp, especially at the edges of cosmology. It is also worth noticing how the language of beginnings influences debates about whether the Big Bang could be wrong. If one assumes that the theory claims to describe the absolute origin of everything, then its inability to see past that origin looks like a failure. If one understands the theory as a description of an early phase of cosmic evolution, then its silence about earlier phases is not a problem. It is simply outside its scope. This distinction often gets lost in public discussions. Critics and defenders alike sometimes argue over claims the theory does not actually make. Clarifying what the Big Bang cannot see past helps ground the conversation in what is genuinely at stake. As you reflect on this, you may notice a shift in how the idea of a beginning feels. It becomes less like a sharp edge and more like a horizon. Beyond a horizon, there may be land, water, or something entirely unexpected. The fact that it is out of view does not mean it does not exist. It means our current position does not allow us to see it clearly. In cosmology, horizons are not just metaphors. They are real features of the universe's structure. There are limits to causality, limits to observation, limits to explanation. Accepting those limits is part of doing honest science. This acceptance does not stop inquiry. It redirects it. Instead of asking for definitive answers where none can yet be given, researchers look for clues that might hint at deeper structures. They search for signatures in the cosmic microwave background, patterns in large-scale structure, and theoretical frameworks that can unify gravity and quantum mechanics. Each of these efforts is, in a sense, an attempt to glimpse something before the beginning, without pretending to know exactly what that phrase means. They are careful steps taken at the edge of understanding, where humility matters as much as ambition. When discussions of the Big Bang reach their most difficult point, they almost always circle back to a single word that carries far more weight than it seems at first glance: singularity. It sounds technical, distant, almost abstract, and yet it marks the exact place where our current understanding of the universe stops behaving like understanding at all. It is not just another feature of the model, it is the point at which the model openly admits that it no longer knows what it is talking about. In everyday language, a singularity sounds like a thing, a point, a moment, something real and concrete. In physics, however, a singularity is not an object that exists in the universe. It is a mathematical signal. It appears when equations produce infinite values for physical quantities such as density, temperature, or curvature. When this happens, it is not usually taken as a literal description of reality. It is taken as a warning sign that the theory being used has reached the edge of its validity. This distinction is crucial because much confusion about the Big Bang arises from treating the singularity as a real event rather than as a breakdown in description. The standard cosmological equations, when run backward, lead inevitably to a state where the density of the universe becomes infinite and the size of space shrinks to zero. That is the singularity. But infinite density and zero size are not physical conditions we know how to interpret meaningfully. They are placeholders for ignorance. To understand why this happens, it helps to look at the tools being used. The Big Bang model relies on general relativity to describe how space and time evolve. General relativity is a classical theory. It treats space-time as a smooth, continuous fabric. Matter and energy curve that fabric, and the curvature tells matter how to move. This framework has been tested extensively and works extremely well across a wide range of conditions. However, general relativity does not include quantum mechanics. Quantum theory governs the behavior of matter and energy at very small scales. It introduces uncertainty, discreteness, and fluctuations that have no place in a purely smooth space-time. Under ordinary conditions, the effects of quantum mechanics on space-time itself are negligible. Space can be treated as smooth without noticeable error. In the early universe, this is no longer true. When densities become enormous and distances become extremely small, quantum effects cannot be ignored. Energy fluctuates violently. The notion of a well-defined geometry begins to break down. Trying to describe this regime using only general relativity is like trying to describe the motion of individual atoms using the physics of solid steel beams. The tool is simply not designed for the task. This mismatch is what produces the singularity. The equations are being pushed into a regime where their assumptions no longer hold. The appearance of infinity is not a discovery about reality. It is a confession of limitation. This pattern is not unique to cosmology. It has appeared before in the history of physics. In classical electromagnetism, calculations involving point charges led to infinite self-energies. These infinities were not accepted as real.